Okay, yeah, thank you very much for the invitation. It's a pleasure to be here. I've just realized I'm really the only one outside the UK, so that's also very nice. Yeah, and I want to talk about world models for control. So basically in a reinforcement learning setup, where we have basically an agent that is interacting with the environment, and we're talking about world models, so it will be model-based reinforcement learning, that we will use the data to learn a simulator or a world model of the world and use that to refine the behaviors. I think we had that already in several of our talks here. And the model that is one of the most common models that is used here is basically the recurrent state space model. That's the underlying model of Trima, Planet, and all these things, which have been also mentioned already several times today. And what does the recurrent state space model do? It basically infers a latent state set given an observation or image sequence and actions. So basically it defines a graphical model that you can see here on the right side. The latent states, you have actions, and also the observations basically directly affect your transitions in this latent state. And this is learned end to end. You basically have an encoder that is basically encoding the image, and you have a decoder, usually learned using reconstruction loss to learn the whole system. That has been used quite successfully in robotics. So this is also not our work, but from 2 years ago, Daydreamer, which directly used that on real robot systems. We have seen a few other examples here already. So just to say, Dreamer works. It's the state of the art in model-based reinforcement learning, and highly used there. But in my talk, I'm not so much interested in now getting into work on a new application. I'm more interested in understanding basic properties and limitations of this model. And first of all, how Dreamer or the state-space models represent uncertainty, or to which extent they can do that, and how we can improve these capabilities, how we can learn good representations using such a model-based approach from multiple sensor modalities, and also how we can extend the long-term prediction capabilities of such state-space models. So these are the three topics I want to talk about today. Okay, so the first work is basically something we did 2 years ago and published on TMLR. It's about uncertainty in the deep state-space models for model-based reinforcement learning. And for that, I first want to have a look at what kind of uncertainty do we have to represent in such models. But first of all, there is the aleatoric uncertainty. And that's due to the stochasticity of the environment. So you can have transition noise, but you can also have partial observability for the current observation. So it's basically two causes. At the same time, there's epistemic uncertainty. So because we have limited data, and basically whenever we don't have data for a certain situation, we are unsure. There's small uncertainty. Typically, so in model-based reinforcement learning, both of these uncertainties needs to be modeled. In Dreamer, it's actually not. So Dreamer doesn't model the epistemic uncertainty at all, and it still works. And we were also interested, why is this the case? Because most other model-based algorithms don't work if you neglect epistemic uncertainty. So why can Dreamer do that? And we have some answers to that. So the question is basically, how do these state-space models model uncertainty, and how can they deal with high aleatoric uncertainty? So let's consider one of the standard tasks, the cheetah, it's standard motor task, isn't it? Quite simple. But if you make it harder and make it only partially observable in a way that, for example, the cheetah is running behind some walls, and sometimes you don't see it at all, sometimes you see only a bit of it. So there's a lot of partial observability now. So it's quite a bit harder. Can we still do it? And the second question is, do we need epistemic uncertainty for doing that? Or how can we trade off both uncertainties properly? And if you look at the recurrent state-space model, which we have here again, our graphical model for that. Then we actually realized that the inference scheme for getting the distribution over the latent state set for a certain time step is actually a simplified inference scheme, and somehow wrong, I would say, or simplified, let's say, because how the factorization looks like, so for getting the distribution of latent states given the observations looks the following, so that it basically says the transition from one latent state to the next depends on the observation. So we see that basically how the errors in these graphical models are aligned. And that's not how you would typically put a state-space model, isn't it? Usually the observation should depend on latent state, not the other way around, isn't it? And because of this assumption, what we will see is that Tremor is inferring a much higher transition uncertainty if there is an observation that it cannot explain by a deterministic transition. So, as a very simple example, let's assume you have a box. You don't know what is inside. There could be a hamster or a cat inside, so maybe Schrödinger's hamster. And so maybe your belief is there's a hamster inside, and then you observe it's a cat. And what the recurrent state space model would now believe is that your hamster transformed into a cat. But a much more logical explanation would be it has been a cat from the start, and the belief here is wrong. But the state space model, the recurrent one, it cannot update the belief at the previous time step. It can only update the transition. So that's why you have this high transition uncertainty in there, turning a hamster into a cat, which is wrong in that case, or maybe the too simplified modeling assumption. So if you look at standard state space models, which are commonly used in control, for example, the state estimation, they look like this from the graphical model, isn't it? So most people will have seen that. So the only difference is basically how the errors are, that's basically how the dependencies look like. And now if you want to do probabilistic reasoning in such a standard state space model, we need to compute again the posterior, the probability of set given observations. You basically need to invert the errors, isn't it? And you can do that by using Bayes' rule, which is basically a classical filtering operation in such a state space model. So, which basically means it's not just one transition, the probability of one transition is changed by the current observation, it's really the whole sequence is changed by observation for time step t. That's obviously more complex to model. So we need somehow a Bayes rule for doing that. And this is, of course, not so easy to implement directly in a deep neural network. So how can we do that? There is a model that's a little bit older. It's also coming from my group. It's called recurrent Kalman network. It somehow does something like that. It's a recurrent neural network inspired by Kalman filter. So you basically have, again, a latent space. And now you have basically also latent observation W, which is basically the encoded real observation. But you still basically in this graphical model you say Z is basically generating W. And what you can do then is basically you can still encode your observations. You get basically a latent observation and the uncertainty of this latent observation, how certain you are about it. And then you can basically define a Kalman update in the latent space. There's another trick in there that we use some factorization assumptions, how basically the variance in the latent space looks like. It looks like it factorizes, and then you don't need to do these matrix inversions that you have to do usually with Kalman filtering, which are very, very, very costly to backpropagate, but it's basically just divisions of scalar values. But the trick is now that you really have basically you represent the mean and the variance of these latent variables using Kalman filtering or Kalman smoothing. You can even do here. And you can either do that with linear models or with local linear models, similar to the extended Kalman filter, and it allows exact inference of the latent state, basically by using smoothing or state estimation or filtering operations. So you can now test this on a very simplified task. So let's say we have a linear system and we want to learn the dynamics, so the system of it. And we compared basically the state space model assumptions with the recurrent state space model assumption, which is the green one, the RSSM. And here, basically, it's a simple task. So we know the ground truth model. We also know the ground truth transition noise. And we can directly see that even for such a simple task, what you get from the RSSM, it completely overestimates the transition noise because of the wrong or simplified factorization assumption. So you could say, maybe that's bad. So let's use the state space model instead of the recurrent state space model, because they have somehow the incorrect inference model. But if you do that directly, it works worse than the recurrent state space model. Even if the model you learn is better, but it works worse. It's like, why is that? It's really a pain to think about it. But basically, the effect that we see is we overestimate the aleatoric uncertainty in the recurrent state space model, and that's why we can afford to not model the epistemic uncertainty. Now, if we model the aleatoric uncertainty correctly, and we leave out the epistemic uncertainty, it doesn't work anymore. So you have to do both things. So the overestimation in the decision uncertainty is somehow counterbalancing another bug, so to say, of the Trimo model, no epistemic uncertainty. But so if you do both, then it works better. And that's basically what we call the variational recurrent Kalman network, which is basically based on these Kalman ideas. But in addition, we model epistemic uncertainty quite simply by using Monte Carlo dropout to learn it. So it's a Bayesian learning method. So and that allows now to do closed form inference and have epistemic uncertainty to really represent both. Okay, good. Then you can test this and throw it into standard control tasks. So this is now DeepMind control suite. And here you see works a little bit better, but it's actually in the end doesn't really matter which one you take, because for the standard tasks where we benchmark all these algorithms, the uncertainty, at least the aleatoric uncertainty, it just doesn't matter. There is no aleatoric uncertainty. Let's make the task a little bit harder. This is now the task I introduced in the beginning with the walls, and there you already see a big benefit. Maybe the other one still works, but it doesn't work that well anymore, the RSSM. And well, you can even do other things where you would believe that should actually work. For example, what you can do is you can just leave out some observations. Yeah? Let's say we only show him every 4th to 8th observation. Yeah? And the recurrent state space model is actually should be built for that, isn't it? So you don't need to observe every time. But you see actually, especially if you have transition noise in your environment, it completely breaks down. You cannot model it anymore. While with the correct inference assumptions, you can still at least, it's a harder task now, but you can still at least learn it. So, and the take-home message here is, so tasks with high aleatoric uncertainty require accurate modeling of different sources of uncertainty. So we need to be able to estimate the aleatoric uncertainty properly and the epistemic uncertainty as well. I think it's a way to understand these models a little bit better when they really work. And if you have high observation uncertainty, then you have to be careful with the standard model-based reinforcement learning algorithms. Okay. So the next topic I wanted to talk about is representation learning in this kind of state space models. And here the motivation is basically that usually in robotics we do have multiple sensors, isn't it? So we have cameras, we might have force torque sensors, we definitely have proprioception, and so on. And these sensors have also very different properties, isn't it? So cameras, it's very high dimensional. There might be a lot of distractors in there, while perception is low dimensional, concise. And the standard way in reinforcement learning, how to do that now would be to use streamer maybe on the image level and somehow concatenate maybe the proprioception and then do reinforcement learning on it. But you can show that this is very suboptimal, and you can learn a joint representation in a much better way. That's what we have looked at here. How can we learn a good representation in reinforcement learning for such multi-sensor systems? And basically what is responsible for representation learning in let's say in Dreamer now is really basically the reconstruction. That we reconstruct the image given the latent representation. At least in the original Dreamer they did it like that. And the problem here is, I mean, it works very well if you have such simple images, but in the minute you put really distractors in there, different background, something that is hard to predict, it doesn't work at all anymore. It completely breaks down. So the original Dreamer model is really designed for such very simple systems. But in these cases, also a lot of the research of the community has concentrated on different representation learning techniques, like contrastive learning techniques, for example, that work better because they can ignore distractions, but are also harder to learn because they often suffer from representation collapse, that everything looks somewhat similar. So, and our idea was now, okay, we have these different modalities, they have different properties. Can we use different representation learning techniques for different modalities? So we use contrastive learning, for example, now to learn to represent the image modality, and at the same time, in the same stateless model, reconstruction to reconstruct the proprioception, which is, there are no distractors, you can directly reconstruct it using the mean squared error loss. And yeah, so that's the main idea. So you have again the state-space representation, latent states. You either have the image or directly the proprioception. Both you want to basically embed into your representation. And for the perception, we use reconstruction, and for the image, we use contrastive learning, which is based on motor information. So you can also formalize that to have basically a status model with multiple modalities. Here we again use the standard Dreamer model. We didn't use the very short recurrent network because it's computationally much more expensive to do that. And there are different ways of training that, using a variational lower bound or using predictive coding, which don't want to go very much into these equations, but basically if you do variational, if you do predictive, if you do contrastive loss, what you basically do is you just replace this reconstruction loss with an info NCE loss, basically, that is doing basically the contrastive error function here. And we tested that in different setups, like one's model-free, where we just use the representation with the soft actor critic approach, so the SAC, or model-based, where we basically use the latent imagination from Dreamer. It turns out actually that model-free is much easier because you only need a good representation. You don't need to be able to predict very well, so that's easier. We had also here two different contrastive variants, the variational biotime and the predictive coding. Maybe that's not so important, but let me show you what kind of environments we used. It's again more the simulated kind of simple tasks, but it's getting more and more like realistic. If you look at the last environment here, so we start with the cheetah with different backgrounds, with different occlusions. So we put some disks on it, some first-person locomotion tasks that you can see here. And this is a manipulation task based on the money skill benchmark suite, where you have basically random backgrounds, and you also need to navigate through an environment, for example, to operate this facet or to open some drawers or something like that. And if you now do that with standard model-based approaches, so this is now the result for the most complex task here, then this doesn't work very well. Yeah, so you could now do the standard concatenation, so you learn the representation of the image using Dreamer, either with contrastive rational or contrastive predictive or with reconstruction, and then just concatenate the proprioception. Yeah. So you get around 40% of success rates. If you use the same loss, only contrastive or only reconstruction, it's also here it's reconstruction would work 40%. But if you basically use this correlate here, which basically means different self-supervised loss function for different modalities, you get up to 70%. So it clearly improves. And all the other reinforcement learning techniques that we tried that you could do on real image data like TRQ, or the repo or something like that, they don't work at all. So it's a quite simple idea, but it really boosts the performance. Okay, good. And the last topic I want to talk about, it's a paper we had last year in Europe called multi-timescale world models. And here basically the question is, how can we extend these models such that they really perform well in long-term prediction? Yeah? Because usually they're only trained for predicting the next time step, and that usually works very well for predicting the next time step. But if you roll it out for, let's say, 10, 20, 100 time steps, the predictions are really usually quite good. And so they are mostly good at short-term prediction. And you also know that the humans are very good at predicting at multiple levels of abstraction, so temporal abstractions or spatial abstractions. And we wanted to use a very similar idea to have multiple levels of temporal abstractions for our prediction. And basically, to have really, again, state space models or prediction models at different timescales. Yeah, so one for the state dynamics, one for the task dynamics, where maybe the task is changing, and one for, let's say, super task dynamics if you really want to have a very slow timescale in there. And so we call this model multi-timescale state space models, or MTS3. Where, I mean, so far we mainly use that with a two-layer hierarchy that you can see here. So you have, again, the fast time scale, which is basically on for every time step you do a prediction given the action. Then you also have the same thing for a slow time scale, where you basically learn a different, more abstract latent state, which we call L. And this more for this more abstract latent state, you also have abstract actions. Yeah, that's somehow a summarized action of the whole time window that you use. Yeah, and abstract observations, beta, that you use here. Okay. And how do both levels interact? So basically, this abstract latent state is directly changing the transitions of the fast time scale, directly reconfiguring basically the state space model. And so, how can we infer this abstraction? So we actually use a quite simple approach here. We take, for the slow time scale model, we take basically the information of H states and H actions and aggregate them together. So it's an encoder that basically encodes each action, and then we basically aggregate them using some Bayesian aggregation technique. We could also use max aggregation, but because we wanted to use a fully heuristic setup here, we used Bayesian aggregation. So it's really Bayesian conditioning on a set of observations. And what you get then is basically, from the encoder, you get a set of H means and variances. So it's a heuristic encoder. you can use Bayesian aggregation to get basically a posterior over the abstract states, and with that you can learn abstract state dynamics as well. Which basically is very similar to these Kalman ideas again. So you have a linear Kalman update here, where you take the posterior, the prior mean and the prior variance, and update the mean and the variance using basically just the Bayesian update in there. The equations don't matter too much, just to get the main idea. And now if you want to connect this layer with the fast timescale layer, what we basically do is, so we have the prior mean and the prior covariance of the abstract state space model, and this is directly used as just as a linear adapter for the fast timescale model, but including the variance. If the slow timescale model is very uncertain, then this is directly induced in the dynamics of the fast timescale model. And there's a single training objective now. You want to predict the marginal log likelihood of the fast timescale observations, but everything is learned end to end in that manner. And it's learned also in a self-supervised fashion that, so we want to predict multiple time steps in the future using imputation. So some of the inputs of the time steps are just imputed, not shown to the systems, and its imputation masks, or it's randomized, and then you basically can learn a very robust model in that case. And so the experiments that we did here are mainly on proprioceptive data. That's not on image data so far, but on quite complex dynamics that have high either non-stationarity or non-Markovianity. So, for example, this excavator data, where you really need to learn the dynamics of a hydraulic arm. It's very hard to model that. So modeling techniques don't work. Such approaches do actually work quite well. And here we have a simulated mobile robot that is going over different kinds of terrain. So you have non-stationary dynamics depending on the terrain that it's simulated. And so what you can basically see here, so we compared our model, this is this MT3 model, with other time series models that we use in deep learning. So for example, LSTMs or transformers and so on. And you can actually see that the performance, especially if you look at long-term prediction, is much better. We can do the same basically here with some standard reinforcement learning tasks where we have a fixed policy now, the learned policy, and we want to predict the future. And you can also see that in this task, for example, in the Frankel kitchen, this multi-timescale approach is really giving you a much better prediction performance, a long-term prediction performance. And you can also look at how do the predictions look like. Now this is for the excavator data. And you see basically here the MT3 model. I mean, it looks a little bit jerky, but it really manages to track the real trajectory very well, while a transformer or LSTM would really have a hard time modeling that. And here the take-home message is that long-term prediction requires modeling on different time scales. If you combine that, you get much more powerful world models. And that's already the conclusion of my talk. So we have seen, we have looked at 3 different challenges for world models in this talk. So first of all, propagation of aleatoric uncertainty requires the correct inference assumptions. So the standard recurrent state-space model assumptions are very helpful in that case. We have seen that representation learning from multiple modalities, you can improve that by using tailored representation learning loss functions for each modality and predicting long horizons tasks. We have seen that these multiple time scales are really beneficial to that. Thank you very much.
Right, we have time for a few questions. the first research presentation. For RSSM, if we when we look at more detailed architecture, the state contains both stochastic state and the deterministic state.
Yeah.
And stochastic state at the moment is only from the deterministic state, and the deterministic back propagation through the deterministic state is done. So it means that a stochastic state distribution information is all of the information is contained in the deterministic state at the moment. So from that sense, even though if we rewrite combined as Z, it seems like factorized. But the actual implementation is not seems like not factorized. It can be correlated over time. So from that sense, how can you explain the compared with your Bayesian update rule for that state update?
So I'm not quite sure I understood the question, but I mean, yes, the RSSM has the deterministic state as well, makes it also a little bit harder to analyze. But we have something similar in the variational Kalman model, because there is basically always the mean. We use basically the mean to linearize the system, so it's an extended Kalman model actually, and that serves basically the posterior mean is also deterministic. That has the same interpretation, I would say, but for us it comes from this Kalman idea, and they somehow, it's kind of ugly the mystic state, but you need it to make it work. Without that, the recurrent state model will not work very well. But we have something similar, but it has a probabilistic interpretation, for linearization.
I see. You mean your work has a more from the aspect of the Bayesian update rule, it follows correctly, so that helps. That takes over than the engineering of using the Arani.
I mean, and the heuristic part of the latent state, it still doesn't help you, isn't it, to get the correct inference. I mean, it's maybe you can put more information in there, but the distributions are still wrong. So that's it.
Okay, so can I ask? So, since like neural network are like universal approximator, in the early days we also used to decoder always used to be inverse of the encoder, right? In the early days of deep learning, 10 years back, right? In that sense, if I say the encoder you're learning is an inverse encoder, or you can then say it's a decoder, in that sense, predicting from the observation to the latent space is the same as inverse of predicting from latent space to the observations. In that sense, Dreamer is doing the correct thing. That's the one question. Yeah, that's the one question. And the second question is, you saying these changes bring the success, but if I argue, Dreamer model always doing discretization in the latent space, but they are not doing the discretization in the observation space. And we know that currently that discretization of the observation space or tokenization helps the learning the representations. That's why you reduce the nodes because of the quantization. So if I argue the function you're learning in between, let's say from observation to the W, and W is coming from that, and that is a just universal function, you divide to the truth function and you do the discretizations, that's why you are getting a better results. What you say to the first question and second. Okay. I'm sorry if it is very fast.
Okay, so it's a long question. So the first is basically that the decoder is inverse model of the encoder.
Yeah.
Not for this, let's say, because here it's not just about one observation, it's about the observation sequence. But the encoder is only encoding one observation, but you also have to take the information from the last time step. So that's quite different. And for that, you use the factorization assumptions in Dreamer, which are the recurrent stages model. And these are wrong because they are using the wrong inference scheme, so they don't compute the posterior property.
The encoder are independent. If, as far as I know, the encoder are independent functions. If you look at the formulations, they are totally independent functions, and they just then they add to the recurrent state space model. So the encoder is totally independent. That is, the abstraction is totally independent of the recurrent state space model.
Yes, but what you need in this is it's a variational model, isn't it? But what you need in variational model is always the posterior. No?
Yeah.
And not just the posterior over one observation. You need the posterior over all observations.
Yeah. That's the inverse function.
And this posterior is based on the factorization assumption on the recurrent stasis model, which is basically, I can show you. So they use exactly this factorization assumption. And this is not how you would compute a posterior in a time series model. The correct posterior by base rule is not defined like that. So you cannot represent the correct posterior with this factorization. The correct posterior.
If I say the Q function is the inverse, still you don't agree? If I say the Q is the inverse of the Q. This Q function, which is like modeling the state space at the time t, is the inverse, if you think on that way.
But here there is no...
Because I can get all the information, OT and like AT is available, because they are in the past.
Then I would need an encoder that is taking all the observations, and the decoder would also decode all the observations at the same time. Then this will work. Yeah? But if you do it with a single, it's a time series model, so it does not work. Yeah, but we can maybe do it offline. Yeah? And the second question
is like you're doing this discretization, your W, what is doing in the between? Is just discretization.
I mean, we didn't use
the function.
We didn't use any discretization here, also not in latent space. So it's a Dreamer 1 model. Dreamer 2 has a discretization in there. We also tested Dreamer 2 on this setup. It also doesn't work very well. Dreamer 2 it works great in Atari for control, not so great anymore. And if you have aleatoric uncertainty.
So you're saying that it works better than Dreamer 2 as well? Then I agree.
Yeah.
Okay. Then I agree.
Quick final question.
First of all, Gerhard, thank you so much. I think that was a great talk. I'm still digesting the first part. You made another comment about your variation recurrent Kalman network, and I think you said you didn't use it at some point because of computational implications. Can you just say a little bit more about that?
Yeah, so it is around a factor of 4 slower, I think, than the RSSM. Because what we basically use in this model is we had this local linear state transition. So which means you first need to compute the posterior mean and then have another network that is giving you the linearization of that, and this is very slow, so you cannot parallelize that properly. And yeah, so we opted for a simpler model because it's already a lot of compute to do these things. Yeah. And also for the benchmarks we used for the second approach, there was not so much aleatoric uncertainty in there. So it was probably there it wouldn't help that much. Yeah.
Let's thank the speaker. We have a very short break. We come back at 3:40. Please.